Hi and welcome. So I thought I'd start this video off with a little story, a backstory explaining my choices over the years. So I was looking for collet chucks for a long time because it makes making medium to small repeatable parts in the lathe really easy. And the first one I ran across was this guy at an estate sale, and so I picked it up because it was a really good deal. And it's a Jacobs chuck, and it uses a whole range of these guys, which I have, and they're interesting because they make metal on metal contact. So there's metal on the outside that meet the taper and metal that meets the part on the inside, and the rubber just keeps them located. When you tighten this guy down here by spinning the wheel, then it compresses. This has a key that it has to meet up with. It compresses all of these guys equally and holds the part centered, and it's fairly repeatable. The only downside to the Jacob style chuck, as you can see, it's increasingly reducing the inside diameter because the rubber just sort of holds it in place. I'm going to loosen it. The rubber just keeps the metal fingers in place, and as you push it down to the taper, the metal fingers move to the inside and grab the part. Now the downside to this guy is that even though you're metal to metal contact, they still can wiggle a little bit this way. And I find that if you put a lot of side pressure on your tool, like you're taking a medium to big cut, you get a little bit of distortion of the chuck center, and the part will move. And what ends up happening is you'll be off by a few thousandths, which was kind of annoying. So it's very convenient, but not ideal. And changing out chucks is really quick, or changing the collets out, I should say, is really quick. Just pop another one in, and this one came with full set, so it was a good find. And then you can lock it by sliding this guy down here. That just locks this ring, so it can't you can't loosen it anymore. But there was another solution I ran across. My next collet chuck, as you can see here, is no more. I sold it. It was a D16 mounted to one of those round with a long nose 5C collet chucks. I don't know if you've seen the type. They sell them on eBay fairly inexpensively, and it worked fine, but it used a chuck key to pull in the collet, and it was just a pain to use. It was very slow and kind of clunky. It worked, so as far as that's concerned, I don't have any complaints, but it was just kind of clunky to use. So I was in love with the hand wheel design over the chuck key, and my next solution was to pick up one of these Atlas chucks, and I really like it. I love the hand wheel. It's very convenient, but there's still a downside to this part, and I ran across this the first time I had to manufacture a bunch of parts for my aerospace guys that like me to make parts for them. I had to make all these parts that were lengthwise within a few thousandths, and that became a problem with this because this style chuck, as you tighten it, you notice it's pulling the 5C collet into the taper. And if you have material sticking out, the material's going back with it, because once it starts to grip, the material doesn't slip anymore and the material will suck in with it. And so you have to be, in order to be repeatable, what I would do is I put a piece of tape on the handle, put a piece of tape on the chuck, draw lines on them, and every time come back to tighten at exactly the same point every time. But it became a pain in the butt, and trying to get better than 5 thousandths accuracy for length was really problematic. So my next solution, after I realized how that didn't work very well, was to find a collet puller. And collet pullers are crazy expensive. To buy a new, what is the brand, like JK or something like that? After you buy all the accessories and everything, just to have the standard collet puller for your lathe, you're looking at almost $2,000. So that was kind of pricing it out of my market. So I found this guy, which is an MSC Industrial, and it's designed for their 14-inch lathes. I thought, oh, that might fit mine. This draw tube is too short, so I've ordered some material to make a longer draw tube, and I'll just thread both sides. However, this guy, which goes out the back of the lathe that the draw tube screws into, this piece here, I wasn't sure that this was going to be the right size. Well, it's not. What you discover here is that my through tube on my headstock is the same diameter of this. This is supposed to slip over that tube. Apparently this lathe is much bigger than a lot of other lathes that are 14-inch, because this doesn't fit. However, I did notice that the spline piece on the end screws to this guy. So I'm going to make a new version of this piece here to fit over this tube, and we'll see if I can make this work. Combined with the draw tube, I think I'll be all right. I don't think there's any other differences for the larger units, because all you're doing is pulling a 5C collet. Oh, forgot to mention, this 5C piece, this is an MT4. I won't be needing that anymore. My lathe is MT6, but I found this one used on eBay a while ago and picked it up. So the outside is MT6 with the 5C collet taper inside here. And so hopefully with all these parts, I can make a working unit. All right, so the 5C collet holder that's for MT5, I'm not going to keep this guy because it's too small. It seems like it's a lot smaller than MT6. I had no idea there's such a big leap there. But it still seems a little bit too large for MT4, because this is MT4, so it's bigger than that, so it's got to be MT5. These are MCO parts. The draw tube also is too short. So I have here some drawn-on mandrel tubing, some DOM tubing, and it's about the same size as this, although it's not as pretty, but it's the same diameter more or less. It's like 20 or 30 thousandths larger external. This guy, pretty simple and straightforward. It's got sort of a cam device you can see in there with the grease, and basically this end gets fixed so that when you pry this guy, it pulls it out, and when you pull it out just far enough, it locks, and that's what holds the 5C collet in place. So this piece here fits in here, and when it's locked, you can't rotate it, but when you flip this little switch down over here on the side, it lets you rotate it, which lets you tighten the 5C collet in place. This is an interesting design. This is, again, the Enco design of this part. And this is the part I got to remake. So I got to remove these 3 screws and pop this very carefully ground and machined part that rides inside here. Got to remove this guy and make a new part here that fits on the back of my lathe where the spider currently is. So let's see, does this just, oh, beautiful fit. Oh, just a very slight relief. Well, that should be easy to remake this part. That's a great fit. Just a thousandth or two slop. So this piece still fits in here. And all I need to do is make the adapter that fits on the back of my tailstock of the lathe where the spider connects. Here's my lathe spider, and this is the part that fits over the back of the tailstock of the lathe. So I only need something this diameter, and that's 3 inches. I found a perfect piece of stock, 3 inches diameter, some 304 stainless. Just facing off one end, gotta make a mess. All right, so this bit is 60 thousandths deep, roughly, and I need to go in 0.402, so I'm just gonna try and take it all at once. Oh, look at that. Wow. First shot. That is, look at that, it sticks. That's a freaking perfect fit. That's amazing. Okay. So we still have to drill and tap the 3 holes in there so this guy can mount on, but we got to flip this over next. We're going to do a lot of drilling before we get to the boring. Stainless is just nasty stuff to deal with. Very gooey, very sticky. You can see it's welded, chip welding's going on there. Well, there goes my drill bit. So we ended up pushing flipping this over and pushing the other drill bit back out the other side. This stuff is just nasty to deal with. This is a carbide tipped drill bit. So I'm pushing it kind of hard. But you can hear that clicking sound? That's when a chip gums up on this thing, I think. And we already have a 1/2 inch hole all the way through this thing. We're just going up to right around 3/4, which is 1/8 of an inch aside. You wouldn't think it'd be such a big deal, but this stuff is just horrible material. Yeah, I don't know if I'm going to risk going up in size. This stuff is just fighting me every step of the way. I think we're going to bore it out instead. I don't want to risk breaking one of these big drill bits, which, just incidentally, if you're wondering, I have done before. Because I got skills. Alrighty, so here's the part, and we just need to drill 3 holes to mount this guy, and we need to put some set screws along the outside of this guy to catch on the rear of the spindle, and then this part should be done. Next up, we need to find the bolt circle for this part, and it's 3 holes. Odd number holes make it challenging. So here is the other part, and I've put the screws back in it. And I can easily measure across here to here, here to here, here to here on the threads and get those chord lengths. But how does that help me find the bolt hole circle diameter for the part? And that's actually a bit challenging. So let me show you some tricks. With the 3 bolt hole pattern, it forms an inscribed triangle with the center of the bolt holes on a circle, and that's the bolt hole circle we are interested in. Now, the only measurement we can easily take off this is from here to here, here to here, here to here. And that measurement will be 1 diameter, or half, 1 radius over here, 1 radius over here, or 2 radiuses total extra, or 1 diameter extra. So if I measure from here to here and subtract the diameter of whatever, like the screws that fit in those holes, that will give me this distance here. And I am going to call that distance X. Let me use a different color. I'm going to call that distance X, okay? Now, if I drop a vertical here through the center of the circle, 90 degrees, that makes this, these are already 60 degrees because this is an equilateral triangle, and it bisects this angle, which makes this 30. Now, this distance right here is the radius of the circle, and that is something we want to know. So if I drop this down so that it's perpendicular, I will bisect this side, which makes this x over 2, and also makes this 60 degrees. So once I have this relationship, let's use basic trigonometry to solve this. So cosine of 30 of that angle equals adjacent over hypotenuse equals x over 2 divided by the hypotenuse, which is the radius that we're looking for. So to get the radius by itself, I'm going to put the radius over here, multiply both sides by radius, which gives me r cosine 30 equals x over 2. And then I'm going to divide by cosine 30 to get r by itself. So r is equal to x over 2 cosine 30. And the cosine of 30 is square root, cosine 30 is equal to square root 3 over 2. Okay, so if this is square root 3 over 2, then what that gives me is r equals x over 2 times square root 3 over 2. The 2's cancel out, leave me 1, which r is equal to x over square root 3. And there's my answer. If I measure x, the overall x value here, and I plug it into this equation, divide by square root of 3, that will give me the radius of the bolt hole circle, and we are good to go. All right, so what I did was I measured across a particular pair of screws, and I found the high spot, which in this case is about 1.741. And I did that for all 3, and I averaged the values. So my circle to circle is approximately 1.741. Then I measured the diameter of one of these guys. Actually, I measured all 3, and the diameters came out to, on the average, of about 0.190. So I have to subtract half a diameter on this side and half a diameter on this side to get this length, which is going to be my x length. So x is equal to 1.741 minus 0.190. That answer is 1.551. So now my radius is equal to x over square root 3, which is equal to 1.551 over the square root of 3. That answer is 0.8955. Carrying an extra digit I probably shouldn't carry. My diameter is twice that. Now, as a sanity check, since I am always doing stupid things, stupid math errors, I took a center finder and put put it in the hole, and then I rotated this whole thing with Dicom on there and created a bolt hole circle on there. Then I took the calipers and very closely measured it, and guess what? I came out to about 1.794. So I know that I'm right in the ballpark. And since the calipers, and I'm just trying to line up with a scratch mark on Dicom, I know that this is a more accurate method. And since I averaged my value, so what I did was when I measured this diameter, I measured all 3 screws and I averaged them together, which means you take their values, add them up, divide by 3. Same for the length from here to here. I did it in all 3 directions, measured them, wrote down the 3 values, added the 3 values up, divided by 3, and that was my average. And I used that average to calculate these numbers. And I think that's going to be much closer than trying to approximate calipers on here, but I'm only off by a couple thousandths, and I'm sure I've got that much slop. So we're going to head over to the mill and drill and tap these holes. All right, we're over here on the mill, going to do the bolt circle. And to rough in the center of this guy, using a Blake coaxial indicator and not having this roughly centered is a big pain in the butt. So what I did was I had this very large countersink and I just roughly got it so that it was centered and zeroed my DRO, and then I'm going to come back with the Blake and get it in tighter. So using that roughing in method, I got pretty close right off the bat. I bumped the table. I was within 1,000th, now I'm like 2,000ths, but still that's pretty darn close. Now I've entered the bolt hole pattern into my DRO, and I don't know if you can see this, but I put a little mark using a center drill just to make sure I was lined up appropriately, and I'm looking there, and the mark is right in the scratch line that I put there, so that's a good backup and verification. So I'm just going to drill and tap a bunch of these. All 3 of these, and then I'm going to drill and tap the sides of this for set screws, and this part should be done. Alrighty, there's the top part. Now I just need to drill and tap the sides, and I'm going to use some nylon inserted set screws in there, or grub screws, so that it won't mar the spindle. Drill these 3 holes and tap them. I used my vise stop with a V-block just to set the horizontal position, make it repeatable, and then I'm using the existing 3-hole pattern to find this 3-hole pattern, and we're on the last hole here, drilling and tapping for 1/428, and that's it. This part should be done. It's interesting to note that the through hole size they drilled was much bigger than the holes they used originally, which was an M5, and I went with 1032. But fortunately, all these screws have to do is prevent rotation and pull away because it's registered on this edge here. So this guy is not really going anywhere. And the holes look pretty darn good. So yeah, the threads are a little dirty on just this one. The other 2 were perfectly fine. So of course, the first one I start with that I'm demonstrating, threads are a little gummed up. So now this part is complete. That'll match with the lathe. Next up, we're going to try to replicate this draw tube. I'm not going to grind the outer surface like this one is. It actually doesn't matter because it just sits inside the spindle tube anyways. But we will thread the ends. Interestingly enough, and I think smart on the part of the people that designed this, the Enco people, the threads in the end, the female threads in the end here for the 5C collets are obviously 5C, but the mating part in the collet puller are also 5C collet threads. So 5C collet threads on the outside diameter are 1.238 by 20 TPI. There's not a lot of great information out there about like major and minor diameter. Well, the major diameter is 1.238. They didn't give the pitch diameter, they gave the major diameter. When I measure a bunch of 5C collets, including a bunch of hard-inch collets, who's the inventor of 5C, they're all over the place. Sometimes they're 1.240, sometimes they're all the way down to 1.22 something. Yeah, they're not very tight. Even the hard-inch ones. I only have older hard-inch ones, but I think that's rather odd considering. But yeah, so we're going to clean up the end here. We're going to remove some material. So this is 1.375 1/8 inch wall tubing. Initially, we're just going to clean up. Wow, okay, this isn't even square. Okay, we got to face this first. This material came from Speedy Metals back east, and you would think that their cuts would all be very square because their machinery is probably pretty well calibrated. At least you would think so. That's way off. Just going to clean up the inside. Now we've got to reduce this outside diameter. Go in 25 thousandths, and we'll go in an inch. I will say this DOM tubing is nicely round. Going to cut some thread relief. So just going to try some threading. First pass, 5 thousandths. Looks good, 20 TPI. Here's the fit up. And this won't meet with this exactly because I have a curved edge there, and I don't think they relieve the inside of this very much. So they don't meet because the flat or the square edge is hitting a curved edge. But we got a good fit there, so we're good to go on this side. All right, so now we're going to do the inside thread portion, and I'm going to make these threads kind of deep so that I can cut some off this end if I need to. A 5C collet only has 6/10 of an inch threads, as you can see there, per the standard. So I'm going to go a little over an inch so I can take some off. But the inside diameter is too big, so I need to remove 50 thousandths. So we're going to start with 20 thousandths. And we're going to go in a little bit over an inch. Okay, we're going to relieve the back of the threads. Okay, should be good to go. This Carmex boring bar has flats on 4 sides, and I know that I've got the quick change tool post square, and so I'm using a 1-2-3 block just to see how square this guy is, and it looks like it's very, very close. I did a scratch pass already, but the threads weren't deep enough to easily check. I'm pretty sure they're right, but we're just going to do an additional 10 thousandths. Yeah. That looks good. I'm going straight in if you were wondering. 10 thousandths passes. So I'm right at 80 thousandths total depth. And I think the total depth actually needs to be about 88. But this time I'm shooting a little short because last time it was a little looser than I would have liked. So I'm just doing some spring cuts here. All right, testing this guy out. That's absolutely perfect. I went 4 thousandths under, and it's right on the money. So there's even a little slop there. It's not even super tight. Normally, as you approach the final depth, I think that's because I was counting the total depth for sharp threads, and these 5C collets are definitely not sharp. They've definitely been rounded off a bunch. This, by the way, is a hard hinge in brand new condition. So I was using that as a reference since Hardinge, as I mentioned earlier, was the developer of this 5C collet style. This is an Asian one. It's even a little sloppier than the Hardinge, but good fit nonetheless. As you see, the threads here only go about so deep, and I actually went in all the way there, so I've got some material I can take off to make this fit right. All right, so there's the threaded pull bar, and it's a little bit long right now. I think it should be like 10 or 20 thousandths too long. So what I need to do is I need to take this chuck off. I need to put the 5C Morse Taper 6, this guy, collet holder in the spindle, and then I need to put this assembly, the bar and puller assembly, on the back, and this won't go all the way in, and I can measure the difference between the face of the spindle and here, which normally has a gap anyways, and I can measure that difference with a adjustable parallel and get a really good measurement of how much I need to take off this. So I'll probably find out what that measurement is and take an additional 10 thousandths off, because this guy here actually fits inside here, and I don't think it needs to go all the way up against the stop. I think it can be back just a tiny bit, because the whole point of this is to pull the 5C collet in. So I'm actually not sure where it's supposed to sit in this relieved range here, but I've got it so that it's all the way forward right now. I can always take some off. That's easy, and I made the threads long enough that that should be no problem at all. First step in this process is to clean everything. You don't want to have any debris in there when you're tightening your taper in, or it's going to be problematic. So let's find out. Let's tap this guy in so it's well seated, and let's go grab myself a parallel and measure between here and here what this thickness, what this distance is here, and then I'm going to pop this guy in and see how far it pushes it out. So this adjustable parallel barely fits in there. Oh shoot, I'm going to have to tighten this guy up because I'm just catching the edge of it. I think I'm really technically out of the range of this parallel here. Another way to do this would be gauge pins at this point, since this is so small, which I might try. Oh, look at that, 0.299. So I went straight for 0.299. It's actually a little bit smaller than that. Oh, look at that. Okay, that's a good fit. I've got the rear assembly in, which now made this guy loose because it pushed it in. And I've got an adjustable parallel in here. And we've set it. And we're coming up 0.377. So now we got to pop the chuck back on, and we're going to take 105 thousandths off this guy. Okay, we're going to take just the end off here. Let's see if that was clean enough. That chamfer was clean enough. Oh yeah, starts nicely. That's good. Depth looks good, and I'm just seeing if I can thread a 5C collet in. Kind of looks like. So you got to pick the depth just before it's going to lock. Oh, I might need to remove a little more off that, because I don't know if I can get quite tight enough. So that adjustment there controls how tight this guy gets, because this is your complete range. That is not a lot. So yeah, I've bottomed out now. So the 5C collet's pulled in, and it's pulled the bar this way all the way in, and I can't. This thing actually needs to go in a little deeper, it looks like. All right, so we're going to take off a little more, because what happened was, by the time these threads bottomed out, the collet wasn't all the way in, so I couldn't pull it any farther. All right, so another fit up. See if I can actually get this one tight. So loose, tight, and I've got range. Nice. So we're good to go here. Handle goes here, and I just need to build a bracket that either mounts on this or attaches inside here. I haven't decided what I'm going to do. I might just glue a big chunk of aluminum on here that I can thread and put a base on for this guy. And this is a quick release thing to remove it, so I can even leave it on when I'm not using it. Rather than drill holes in the headstock of my lathe, which I really did not want to do because I don't know what's on the other side, and getting this top part, it's pinned in, so it's pretty difficult. I wasn't able to get off last time, although I didn't try too hard, because that could destabilize the shape of the whole headstock by small amounts, and then I'd have to re-true the lathe. So rather than drill holes in this, I didn't even take off the paint. I roughed up the paint, and then I epoxied this 1-inch thick plate of aluminum on here. And I'm going to use that to mount this guy too. So once the epoxy is done curing, this guy is going to go right like this, and there's a hole right there. So that should be no problem. And I've also got to identify where the hole is on the side of this guy, which is roughly where that square plate is, but I need to mark it. So after the epoxy's done curing, I'm going to come back in here, and I'm going to mark on this aluminum plate where that round hole is so that I can make sure that this shaft clears, although I already tested it and it clears pretty easily. And then I'll just drill and tap this aluminum plate, and we should be good to go. There's not a ton of pressure on this. Then I can leave this guy installed with this piece and pop this pin out here to remove this thing when I'm not using it. It's got a cotter pin in it right now, but I'll take that out. Maybe I'll make some larger pin on this. Just so it's a little more convenient. And after I do that, should be done. We've bolted the pull arm stop bracket to the aluminum. I drilled and tapped these holes. First I put in one, made sure it lined up with the hole. It actually was shifted over this way quite a bit because this comes at an angle. So we were able to get it first shot, which is good. And the epoxy is holding nice and tight. Plus, most of the force is pushing in towards this, towards the headstock anyway, so that shouldn't matter. So I'm going to put the cover on, see if we can get this thing adjusted. This rod's a little bit short, but the threads are a very strange size. So I'm not sure. It's not half 13, and it's not the metric 12. So I'm not really quite sure what it is. All right, so here we are complete. Loose, tight, loose, tight. And it would have been nice if this hole had been down here, except the pulley is down here, the main pulley, so they couldn't have put it down there, but that would have made the arm up and easier to reach. So with the size of this lathe, it's actually hard for me to be at the part and grab this at the same time, but it is working nicely. Show you the front side. All right, here's loose. Pop the handle back. Nice and tight. Make it loose, pull it out, go to the next part. Very convenient, and the advantage is that the mechanism in back sets the depth this 5C collet goes in to be the exact same every time. Alrighty, here we are at the end, and the collet puller is installed. The only regret I have is the angle of this guy being down, but that's where my pre-done hole was, and I couldn't go low because the pulley's there anyway, so I couldn't just drill another hole. I might find another way to mount a plate on this fiberglass here big enough that it gives it some strength, because it's actually a fair amount of force when this is going in and out to engage that. So this does flex a bit, but maybe if I put a big metal plate on here and glue it to that, that'll be adequate, or screw it to that, something like that, probably maybe both. In any case, this works. It lets me set fixed depth parts repeatably, and that's exciting. And it found that helped me know that the Enco, which is designed for smaller lathes than mine, can be modified to suit this larger lathe. And so maybe you'll be lucky too. Now be careful, the draw tube inside on some of the models like the JKL, JFK or something like that, I forget what the brand is, but the big brand out there, that model, some of theirs, the pull tube is brazed in. And if it's brazed in, that'll present a problem for you, make it a little more difficult. This one's threaded in, which I am going to have to Loctite at some point. But in the meantime, I am very excited, and this has been a good project. Thanks for watching. Hope you find it useful. Hope to see you next time.